In this video, we're going to discuss some of the uses for radiation. Radiation actually has several types, and the term can have a mix of meanings culturally depending on where you're from. In general, folks tend to have a somewhat social fear of radiation. This stems from a lot of misinformation that was provided during the Cold War and the rise of the use of radioactive materials. While Madame Curie and others had pioneered the research with radiation early on, it was really the end of World War II and the use of the atomic bomb that brought it into public's awareness. During the Cold War, various countries were detonating a lot of bombs. People were a little hesitant. They kept being reassured, don't worry, there's not that much radiation. And then people would get sick in the surrounding areas. And so folks got this idea that it didn't take a lot of radiation to be really, really dangerous. There's a lot of more caveats to it than that. A lot of time, the radiation from detonation wasn't too bad. It was far enough away, but the fallout that came, that was a different story. So let's explore what it takes for radiation to be harmful, how we can use it before it's harmful, and some of our considerations. So what are some of the uses of radiation? First off, we need to talk about the types of radiation and their differences. An alpha particle, it's large, it's slower, and it's less damaging. Why is that? Well, it just doesn't get very deep. Alpha particles are large enough that they tend to bounce into other things and stop pretty quickly. Your clothing is often enough to stop the majority of any alpha radiation source. Now, it's always a percentage, and if your source is great enough in concentration, then it may not matter what protection you have. But as a general idea, alpha radiation is not terribly dangerous by comparison. Beta radiation, it's smaller, it's faster, and it's more damaging, so it's fairly middle damage. It's an electron. It's moving a good chunk of the speed of light. It can smash into molecules in your body and start to break bonds. So if you have a cell and it's got your phosphodilipids making up your cell wall, and then you got your inside of the bilayer. Well, if you've got an alpha particle, it can hit and it can smash and it could do some damage, and it tends to stop pretty quick. Maybe it gets partway into one cell, but your body has 1 trillion cells. It doesn't do a bunch of damage. And even if it messes up a few molecules, your body can recover from a little damage. You're constantly taking every nick and scratch and bounce and bump against a wall. We get bruised and cut and everything fairly often enough in life, and we just heal from it. Your body takes some damage all the time. Alpha particle doesn't do too much, and your body can deal with it. Beta particle, well, that can dig deeper, hit more things at different depths, and so it could get many cells deep into your body. It can transverse farther, hit more living material, do more damage in more places. It can even make it and hit your DNA much easier. DNA damage can cause mutations, maybe cause the cell to go through apoptosis if it's trying to divide at the time. And so beta particles, because they can dig deeper due to their smaller size and faster travel, they tend to cause more appreciable damage in a biological system. Gamma radiation, this doesn't really have a size, it's a photon, and it is the most damaging. Effectively, it's just pure energy. Your gamma particle can cut straight through, dig quite deep. In fact, often a good portion of them can pass right through you. Some don't deposit any energy. Many can deposit lots of energy. Some are completely absorbed. These can break lots of bonds. Many, many molecules can have damage done to them along the way. Many little proteins and chunks of DNA can be broken. Gamma radiation is significantly more dangerous to a biological system as a result. They are penetrative. They can pass through, hitting things all over. Especially for multicellular organisms like humans, this is a problem because alpha and beta tend to stop in our outer layers, but gamma can hurt our internal organs. If your skin suffers a lot of damage, our skin regrows, at least if it's not too badly damaged. And so over time that heals up. But if your kidney gets significantly damaged, there's not much we can do about that. And so because gamma can penetrate, it tends to be more damaging and more risky for a biological system. But as with all things, it's about the amount. We take damage all the time. You're made of trillion some cells and you lose 50 to 100 million a day. Add a couple 100,000 onto it and it's like you fell and scraped your knee. As long as the radiation isn't doing too much damage too quickly, our bodies can process it. In fact, we're being bombarded by radiation all the time because there's types of radiation. There's electromagnetic radiation and there's nuclear radiation. Now, we've discussed nuclear radiation, the alpha, the beta, the gamma. Well, gamma is technically also part of the electromagnetic. It's a photon. Electromagnetic spectrum has our infrareds, our radio waves, our visible light. All of those, the low energy, radio, IR, visible, these generally are considered non-ionizing. They're generally not strong enough to break chemical bonds in biological systems. Organic molecules tend to be resilient to these amounts of energy. Above that, though, ultraviolet, or X-ray, or gamma, these are ionizing. These are strong enough that they can break the bonds. And so plenty of radiation we're bombarded with constantly cannot damage the molecules in us. They don't have the energy to break those bonds. But there are definitely types that can. This is why you get a sunburn. Ultraviolet light is strong enough to break organic bonds. And so it starts damaging your cells, breaking the cell walls, causing some cell death, which is why we then get blisters and red irritation as our body responds to it. And yet we take X-rays all the time, and we're not generally worried about it. You get the little lead apron at the dentist, and then that's it. The dentist uses it all the time. Does X-rays not damage us? Well, yeah, it does. Just not enough to matter. Lightly scrape at your skin. You maybe did a little damage to your skin. If you did it for an hour, it'd probably hurt pretty bad, but a little here or there doesn't really add up. X-rays were a fantastic discovery, and one of the first ideas widely used for using a source of radiation for medical imaging. That was one of our first major uses of radiation. Imaging. Especially in medical situations, you've got a source that can fire X-rays out. You have somebody's arm, and they hit the arm. Most will pass through. Maybe lost a little energy. Most of the time, simply weren't absorbed. There was no transition that was really able to absorb them. However, X-rays are strong enough to knock electrons off of things, and so some of them do get caught and absorbed, and an electron gets completely ejected. So there are some ejected electrons. Much lower energy than we think of for beta particles, but they get kicked off. You do ionize some of the bonds, some of the atoms in your arm. This hits our film, and they start to pile up. Anywhere that X-rays got through quite readily, we get a signal. But there'll be spaces that are kind of dark. Fewer X-rays got through. Well, when we invert this and take a negative, what we see are those formerly spots where very few X-rays got through. And what we find is that it's the bones. Calcium and the bones are a lot denser than the surrounding tissue, mostly made of water. The denser the material, the more likely the X-rays to get absorbed. Calcium has a lot more electrons on it than carbon and oxygen. And so we see the X-rays get absorbed by those bones, and then we can see the bones. And if there happens to be a break somewhere, well, some of the light might get through. Might find a little gap. When they first discovered this, people had never really been able to see a skeleton of a living thing. In fact, the phrases at the time were things like, "I've seen my death," when you could see your bones, because there was no other time you would ever see the bones of a person. And introducing this as a means of medical science took a little while as people were a little hesitant. Today, we tend to be a little hesitant due to the thought of radiation. But again, it's really the amount. Modern devices don't even use film anymore. You don't have to have a chemical reaction. Charge capture devices that are used for modern X-rays are extremely sensitive, which means we need far less X-rays than we did in the past. The amount of radiation is very minimal and simply not enough to really harm us compared to whatever damage you did already to break that bone. A little bit extra added by X-rays is not meaningful. But carrying down to other things, let's talk about gamma radiation. There's actually a lot of uses of radiation for cancer. Historically, radioisotopes used for cancer treatments was a spin out of the public relations campaign from the Cold War. We were making all these bombs. We had all this leftover radioactive material. Hey, let's make some medical advances for it. It's actually been a big problem since the end of the Cold War. We're not making as many bombs. We don't have as many radioactive isotopes available. We're not producing them as much. Many medical procedures became a lot more difficult. There's a couple that we have only 1 or 2 places on Earth that make the isotopes still. When a Canadian facility went down for a while, we simply couldn't do certain cancer treatments for a year or 2. So we've been developing other ones that are a little bit more accessible in recent years. One I like to talk about is the gamma knife. So if you have a person and let's say they've got, unfortunately, a tumor in the brain. You've used some positron emission tomography. You saw the positron collide with an electron, explode in gamma radiation, and you saw the location. Problem is, it's inoperable. There's no way we can reach that position with surgery. And it's too large at this point for chemo to be successful. Chemotherapy tends to cause cells that are trying to divide to die. Cancer cells try to divide constantly, so they tend to be doing it at any given moment, where other cells might wait quite a while before dividing. So if you give a chemotherapy drug, any cell that tries to divide ideally will die. Mostly the cancer cells will die, but a little bit of damage happens everywhere. It's a fight between having the cancer die off before it does too much damage to the rest of the patient. We can help this if we can reduce the amount of the cancer cells. Well, you could blast gamma rays, but if you do enough to just kill all the cells there, you'll do the same amount of damage as if you tried to commit surgery and remove that chunk. Instead, you give just a little gamma radiation. Not enough to destroy any cell along the way, but just to hurt them. They'd have to heal. And then whatever device you're using, you move and you do again. And you do again. And again. And again and again and again. And if you've got a really well-made device with a very narrow band of gamma radiation coming from it, you can overlap them on a target area. This means that any cells along the path that isn't at the site of overlap don't get enough radiation to suffer greatly, but the ones that are on the overlap accumulate a great deal of damage, enough to cause them to be destroyed. This is good enough now to remove cubic millimeters of cells. And so we can remove very tiny sections inside where we'd never be able to operate surgically. This means that you can reduce the amount of tumor immensely before engaging in chemo. And a mix of radiation therapy and chemo is a very common method these days for cancer therapies. All this has been using the radioactive byproducts, the emissions, the alphas, or the positrons and the like. There is some use for radioactive material directly, though it is far less common. Generally, we're using the radiation, not the radioactive material. One special exception, I-131. Iodine, we need a tiny bit in our body. If we don't have it, we get goiter. And so goiter, you got a person, and what will happen is the thyroid will start to grow. Reason why is the thyroid produces a few chemicals our body needs that have iodine on them. If our body starts to see that we don't have enough of those chemicals, it sends a signal and tells the thyroid, hey, you need to up your production. Now, this happens especially when we're younger. The thyroid gets bigger as we get bigger. Problem is later in life, especially if you don't have iodide, you're not getting the molecule. The body will send the signal, the thyroid tries to get bigger, but that doesn't help because you don't have iodide. That results, you get a runaway effect where your thyroid grows and grows and grows, and eventually it can restrict your airway. Modern world, this isn't really a problem. We ship iodide inland. It's in all of our salt for the most part. That tiny little bit added is enough to satisfy all the needs for the body. Goiter from this source is very rare in the modern world. There's still some places that don't get iodinized salt. This can be a problem inland. But hyperthyroidism is still an issue. Other medical reasons can cause it. Problem is, if you've got a bunch of cells, well, even though you could try to surgically go in and remove them, they'll scar. If you take out a chunk of them, you'll just get a scar built up on it. This can be problematic, not to mention there's a lot of veins and arteries in the neck, nerves. It's not a great place to be doing a lot of surgery. If things scar over poorly, then you also have weak points, and your throat's always working to try to talk or try to eat food or drink. This is a problem. If, however, you can let it kind of naturally lose cells, just one at a time, well, cells tend to move a little bit. They'll move in a little, and then another one can get cleared out or two, and things will kind of contract a little bit. If naturally cells are able to remove themselves just a little at a time, you can get something to shrink instead of scar over. So we need a way to remove cells bit by bit, and that's where radioactive iodine comes in. You give a person iodine that, while spread out through the whole body, wouldn't be enough to be a concern. Because that iodine is going to concentrate in the thyroid, what wouldn't be a problem spread out everywhere now concentrates down from, say, 90 liters of human volume into a quarter of a liter. Now you're over 100 times more concentrated, and now that level of damage might be enough that it starts taking out a cell every once in a while. So you give somebody a little bit of radioactive iodine, it shrinks the thyroid. You give them a little more, it shrinks the thyroid. You give them a little more, it shrinks the thyroid. And when it's small enough, you just stop. Now regular iodide is all that's left. That's non-radioactive. You have a healthy person with a normal thyroid. And so while there are some uses for actual radioactive material directly in the body, most of the time it's just imaging. We're giving somebody a sample so that we can see things either passing through or coming out, whether that's positron emission tomography or some of the barium salts that we use to observe people's arteries to see where there may be a stroke in a stroke patient or things like that. There are many, many uses for radiation in common medical procedures. We also use radiation in a variety of other ways, numerous beyond the scope of this course, but here's a few common medical procedures for the uses of radiation. Since we tend to be worried about its effects on us, how is it that we're able to use it safely to actually benefit us?